today we are going to be talking about how to determine whether or not a set table of points is linear or nonlinear, aka how do we find the slope from a table. That is what we're going to be doing today. We're going to be reviewing how to find the slope from a table, and we're going to take it one step further to determine whether or not it is linear or not linear. So, real quick, let's just jot down some definitions. If we have a linear function, then that means we have a constant slope. So in order to be a linear function, we have to have a constant slope, meaning if we look at the set values in a table, we can determine the slope throughout the table, and it's constant. So nothing new here. Now, if it's a non-linear function, so a non-linear function, it means that we do not have a constant slope. No constant slope. So this is going to be when our slope is different throughout the table, when the overall value of our slope changes from each set of data points. So before we've talked about, hey, can we find a constant slope, yes or no? Now all we're doing is taking it just one step further, and we're saying, is this a linear function or is this a non-linear function? And again, a linear function means that we have a constant slope. A non-linear function means that we have no constant slope. So without further ado, let's begin. So is this function below a linear function, and how do you know? Well, again, to be linear means we have to have a constant slope. And we know how to calculate the slope from a table. We know that our slope, m, is equal to the change in y over the change in x. So we want to calculate the overall slope from each set of values. So to do that, we're going to look at all of our y values. Well, we start with the first value of 5, and that increases to 8. How did we get there? We add 3. We go from 8 to 11. We add 3. We go from 11 to 14. We add 3. So it looks like we have a constant change in our y value, which is going to be equal to positive 3. So now we need to see, do we have a constant change in our x value? Well, let's look at our x values to determine it. We start with the first value, which is 1. That increases to 2. How do we get there? By adding 1. Go from 2 to 3. How do we get there? By adding 1. And we go from 3 to 4. And how do we do that? By adding 1. So we have a constant change in our x values, which means our change in x is 1. And it's the same throughout, which is good. We have to make sure all of these are the same throughout. So the first change was positive 3 over positive 1. The second change was positive 3 over positive 1. And our third change was positive 3 over positive 1, which means we have the overall same value, which is very important here, that those values are the same, right? These also look the same as well. They look the same, and the values are the same, which is very, very important. So this was one example of how to determine whether or not the function is linear, and how do we know? So we calculated the slope, and we know because we would say it's linear because our constant slope is 3 over 1, which again, we could simplify down just saying 3, because 3 divided by 1 is 3. So that's how we would approach this kind of question. Awesome. In this example, it's the same exact question. Is this function below a linear function, and how do you know? So again, let's go back to what we know definitively. We know that slope is equal to the change in y over the change in x. So we want to calculate the change in y and then separately the change in x. So we look at our first y value, which is 2. Go from 2 to 9, which means we added 7. Now we go from our second value to our third, so 9 to 16. Well, we added 7. Now we go from our second to our third value, our third to our fourth value, 16 to 30, and we added 14. Now I notice that we increased by 7, and then by 14, which is weird because we're not increasing by the same value, but that's okay. We're now going to go and calculate the change in our x values and see if we have a relationship, if we have some kind of constant overall value. But before we do that, what I'm actually going to do is I'm going to write each change that occurred. So we actually only have 3 of them, not 4 of them. Whoops. So the first change in y was 7. The second change in y was 7. And the third change in y was 14. So now we're going to calculate the change in x's and put them in their respective areas. So this is what I mean by that. We're going to start out with our x value, so 0 goes to 4. And the way this happened was we added 4. Well, in that first change of y was 7, so we have 7 over 4. If I were to highlight this to show you visually even more, it was 7 and 4, that's this value. Well, now we go from our next change, 4 to 8 is plus 4, so we move on to that second change. Let me highlight again just to show you where these values are going. And now we're going to continue. 8 to 16 is plus 8. Let me erase that plus sign because we don't leave a plus sign there. But one thing that I do know is that I can simplify 14 over 8 to 7 over 4, which means that I can simplify this third rate of change, 14 over 8, into 7 over 4. So what is the constant rate of change here? It's going to be 7 over 4. We go up by 7 and over by 4. So our constant rate of change is going to be equal to 7 over 4. And since we have a constant rate of change, we would say this is linear because our constant slope is 7 over 4. So although the increases looked different, they have the overall same value. 7 over 4 is the same as 7 over 4, which is the same as 14 over 8 because we can simplify 14 over 8 to be 7 over 4. So although the increase in y and the increase in x were a little bit different, they have the same value. It's like saying 5 pennies is equal to 1 nickel. It's still worth 5 cents. They just look different, but the overall value is going to be the same. Awesome. Let's go through one more example. So again, it's the same question proposed. Is the function below a linear function, and how do you know? So we're going to go back to calculating our slope. So our slope is equal again to our change in y over our change in x. So let's see if we can calculate these changes in y's. Well, I'm going to have 3 changes, so let's put them down below. My y values go from 5 to 10, which means that first change is plus 5. We go from 10 to 13, which is going to be plus 3, which again, it looks different, but it might have the same overall value. And then we're going to go from 13 to 20, meaning that we went up by 7. So that third change is going to be positive 7. Now, none of the changes in the y values are the same, but that's okay, so long as the change in x values give us the same overall value. So now let's go and check it out. We go from 0 to 1, and that's by adding 1. So that first set was 5 over 1. So in order for us to have a constant slope, we have to have the overall value of 5 over 1. So let's continue to see if we get that. From 1 to 2, we added 1 again. So now this second change went up by 3 and right 1, meaning that we have the overall value of 3 over 1, which to me seems a little bit fishy. Then we go from 2 to 3 by adding 1 again, which means that this third change was 7 over 1. So is 5 over 1 equal to 3 over 1, which is equal to 7 over 1? No, it is not. So since we do not have a constant rate of change, then we do not have a linear function. This is going to be a non-linear, again, because we do not have a constant slope. So since we did not have a constant slope, the overall values of those changes were not the same. This means we do not have a linear function. So we have what we call a non-linear function. So that is how, again, we find the slope from a table. And then we're taking it one step further by saying, okay, now that we find the slope, is it a constant slope? If it is a constant slope, then that means we have a linear function. If it is not a constant slope, that means it's a non-linear function. Great job, folks. If you have any questions, please let me know. Keep up the good work, and I'll talk to you soon. Bye.